Okay, today we're going to work on the problem set from chapter 7, which is energy and energy resources. And we'll also be discussing power. And the first problem we'll be working on is problem number 4. And it says the following. Suppose a car travels 108 kilometers per hour, 108 kilometers at a speed of 30 meters per second. And uses 2 gallons of gas. Only 30% of the gasoline can be converted into useful work to move the car and so forth. And using table 7.1 for the energy value for gasoline, it asks what is the force that is carried if the car travels at a constant speed. Okay, so let's take a look at this problem. So the distance we're going to travel here is 108 kilometers, which translates into 108,000 meters. And whenever I have things like that, I always convert them to meters if I can. And it's 30.0 meters per second. You realize that this has 3 significant figures here as well. And there are 2 gallons of gas. Now, looking up in the table for the value for a gallon of gas, it's 1.2 times 10 to the 8th joules per gallon. And so if we take that, the total energy is going to be 1.2 times 10 to the 8th joules times, we have 2 gallons, times 30% is converted. So if we do all of that, we get 7.2 times 10 to the 7th joules that is available to do this work. And the work is going to be equal to the force times the distance. So that the force is now going to be equal to the work divided by the distance, which is equal to 7.2 times 10 to the 7th divided by 1.08 times 10 to the 5th. Now if you do the math here, you get 670 newtons of force. The next problem is problem number 7. And problem number 7 states that a shopper has a grocery cart and pushes this grocery cart at a constant speed for 20 meters on level ground. And there's a friction force of 35 newtons. And the question here is, if the angle of the applied force is 25 degrees off horizontal, what is the force that's applied in order to achieve this amount of work? So the first is you have work is equal to the force times the distance. Now the fact that the force applied is off center doesn't matter, because what you're doing is overcoming the friction force, and that's the work that's being done, is overcoming friction. So it's going to equal 35 newtons times the 20 meters that it travels, or 700 joules of work. Now the second question asks, what is the work done on the cart by the gravitational force? Well, in order for the work to be done, you have to have movement. This would be the weight, but you have to have movement in that plane, and there is no movement in that plane. So it's going to be the weight of but it doesn't move in that plane, so there's no work done in that plane. C, what is the work done on the cart by the shopper? Now, this is the point where we have to take into account the total work. The total work here is going to be this work done against gravity, which is nothing, and then the work against friction, which we've already decided was 700. And so this also is going to be 700 joules. The next question is, what is the total, or excuse me, find the force the shopper exerts using energy considerations. Now what it means by when it says using energy considerations is that the fact that we have an angle of 25 degrees now. And so the force that the work is done is the force that is applied times the distance, but there's this cosine of the angle theta, because the angle, the direction is, this force is going to be what moves it is the parallel force or horizontal component of this force, or the x component of the total force. And so the force applied by the shopper is going to actually be this 700 divided by 20, which would be basically the 35 that we had up here, but then also the cosine of 25 degrees. And so that increases this to 38.6 newtons. Now the other way to do this is to just say this is the friction force, which represents this x component, and if you divide that by the cosine of 35 degrees, then you get the actual total force. And then the last question, what is the total work done on a cart? Again, the total work done on the cart is going to equal the work to overcome friction plus the work of the shopper. And the work to overcome friction is 700, and the work the shopper does is 700, but in the opposite direction, so the total work is 0. The next problem is problem number 12. Calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour in a distance of 120 meters, a fairly typical distance for a non-panic stop. Okay, so now using energy consideration, the way to do this is to say that, well, first of all, let's convert the 90 kilometers per hour to feet per second, or meters per second. If you do that, you get 25 meters per second. And then the work done is equal to force times distance. And that's also going to be equal to the end kinetic energy minus the initial kinetic energy, which is going to, and the end kinetic energy is 0 because it's going to be stopped. Velocity at the end is 0. So you end up with minus 1/2 the mass, which is 950 times 25 squared. And if you do the math here, and then that's going to be equal to the work, then if you want that's going to equal work times distance. So if you want, or force times distance, if you want the work force, you have to take this number and divide it by 120, because that's the distance that it stopped over. And so if you do the math here, you get a minus 2470 newtons. So the second part of this problem is the same calculation. It just says that it hits a concrete abutment and it goes from the speed to stop in 2 meters instead of 120 meters. And basically everything is the same except this number is now 2 meters. So we have minus 1/2 950 times 25 squared. Now it's going to be divided by 2 instead of divided by 120. If you do that calculation, you get minus 1.48 times 10 to the fourth, or fifth, excuse me, newtons. And if you compare these two, if you put the second one in the numerator and the denominator is 2470, it's 60 times greater force is imparted by the brick wall to stop than was imparted by the casual stop that occurred before. The next is 13. And number 13 states the following. A car's bumper is designed to withstand a 4 kilometer per hour, 1.1 meter per second collision with an immovable object without damage to the body of the car. The bumper cushions the shock by absorbing the force over a distance. Calculate the magnitude of the average force on a bumper that collapses 0.2 meters while bringing a 900 kilogram car to rest at an initial speed of 1.1 meters. And we do this exactly the same way as the previous. We take the net work performed and that's going to equal the final kinetic energy minus the initial kinetic energy. And again, because we're bringing it to a stop, this is going to be 0. So the net work performed is going to equal minus 1/2 mv0 squared. And that work is going to equal the F times the distance. So the force is going to equal mv0 squared over 2 times d. And that moves this 2 down here. And so we have a 900 kilogram vehicle that goes from 1 point, and the initial velocity is 1.1, and that's divided by 2 times the distance, which is 0.2 meters. And the force that it absorbs in that process is going to be minus 2,700 newtons. Number 16 is our next problem. Number 16 states that a hydroelectric facility, see figure 738, converts the gravitational potential energy of water behind the dam to an electrical energy. What is the gravitational potential energy relative to the generators of a lake of a volume of 50 cubic kilometers, with the mass being 5 times 10 to the 13th kilograms, given that the lake has an average height of 40 meters above the generators? Okay, so basically the change in potential energy, gravitational potential energy, is going to equal mgh. That is the mass and gravity, and then the difference in height. The mass and gravity stay the same, so what we're looking for is the change in height. In this case, that's going to equal 5 times 10 to the 13th kilometer, or kilograms, times 9.8, which is gravity, times 40 meters, which is the change in height. If we do the calculation here, we get 1.96 times 10 to the 16th joules of power. Now it says, the second part of this says to compare that to the energy in a 9 megaton fusion bomb. And if you look at there's a table in the book, A 9 megaton fusion bomb has an energy of 3.8 times 10 to the 16 joules. And so if we put that in the denominator and put our previous 1.96 times 10 to the 16 in the numerator, we see that this energy produced is about 0.52 times as much as the energy of the bomb. So it's about half as much energy stored in this lake as in the energy of the bomb. Let's do one more problem before we switch to a new video. And the next problem is problem number 21. Problem number 21 states that a downhill skier, surprisingly, there's little advantage to getting a running start. And so the downhill skiers, you see, that do all this running to get going, it really doesn't make as much difference as you would think. And this is basically because the initial kinetic energy is small compared to the gravitational energy that occurs going down the hill. To demonstrate this, find the final speed and time for a skier who skis 70 meters along a 30-degree slope neglecting friction. Okay, so you have a distance of 70 meters and the slope is 30 degrees. And so what you have here is the 1/2 mv0 squared is the initial kinetic energy that this person has by taking off running. mgh is their potential energy. So in this case, we're going to calculate this based on v0 equals 0. So they don't take off. So this is gone now. So now all we have is this. And so, and this quantity equals 1/2 mvf squared, or their final velocity squared. And as it turns out, we can get rid of the m's because they're on both sides of the equation. We solve this for the, vf, and we end up with 2 times gh, and the square root of 2gh in a situation where v0 is equal to 0. And that's going to be vf. Now h here is going to equal to the 70 times the sine of 30 degrees, and it turns out the sine of 30 degrees is 0.5, so it's 35. So this is going to equal to 2, the square root of 2 times 9.8 times 35. And if we do the math here, 2 times 9.8 times 35, that's going to be 26.2 meters per second. Well, what we can use is that the distance that they traveled for the slope is equal to v0t plus 1/2 gt squared. And we know this is 0 because v0 is 0. And so if we turn this around, the t is going to be 2d over g square root, which is equal to 2 times, now d here is this original 70 divided by 9.8. And if we do that math here, we have to take into account the person's g goes straight down like this, and the actual acceleration is going to be related to the parallel force here. So this is actually going to have to be multiplied by the sine of 30 degrees. And so if we do that, we get 5.35 because all of the weight is not used to propel them down the hill. it's only the parallel component, and the parallel component is the sine of 30 degrees. If I can draw that a little better, here's the weight, there's the normal, there's the weight, and there's the parallel. And the parallel component is the sine, is the hypotenuse times the sine of 30 degrees. So the acceleration is going to be the hypotenuse, the sine of 30 degrees. So the time is going to be 5.35 seconds. Now the second part of this problem takes the same calculation, but starts out, we can't leave this out now. So we have 1/2 mv0 squared plus mgh is equal to 1/2 mvf squared. And the m's cancel out across the board here. And we have 1/2 v0 squared plus gh equals 1/2 vf squared. And we multiply it through by 2, we have v0 squared plus 2gh equals vf squared. So vf is going to equal to the square root of v0 squared plus 2gh. We put that in. It says that the initial speed is 2.5 meters per second squared plus 2 times 9.8 times 35. And it turns out that it only increases the velocity by 1/10 meter per second. And if we plug this into this formula, v0t plus 1/2 gt squared, the calculation becomes a little more and so actually the best way to do this is to say that the average velocity is v0 or vf minus v0 over 9.8 sine theta. So that's the average velocity increase divided by the acceleration is going to equal to time. So basically what we're saying here is time is equal to the average velocity times the acceleration. And so t is going to equal 26.3 minus 2.5 over 9.8 sine 30 degrees. If you do the math here, you get 4.86 seconds.